So for B1, this is similar to a question that was on our tutorial. Here, what we're asked to do is we're asked to compute t of a really big number. And we don't like solving for really big numbers. So what we're going to do is we are going to see if there's some sort of pattern. So I'm just going to start by writing what t of x, y, and z is. This equals z, y, x. Then what I'm going to do is I'm going to look at what t2 of x, y, z is equal to. And this is equal to t of z, y, x. And now here, z's going to go to the last term. X is going to go back to the first term. So this is going to be x, y, z. This is equal to I of x, y, z. And I see some sort of pattern has developed. So t squared of x, y, z is equal to I of x, y, z. Thus, t of x, y, z is equal to, or tn of x, y, z is equal to tn minus k, or n minus 2k of x, y, z, where n and k are integers. So I can keep subtracting off 2k's from this massive number. So t to the 15.333 of x, y, z. As long as the other expression is odd, it will be the same. So this is equal to t of 15.33 minus 15.32 of x, y, z, as this is an even number. So it's a multiple of 2. So this is equal to t of x, y, z. Thus, as 152 or 1532 is even, thus t 1533 x, y, z is equal to t x, y, z, which equals z, y, x. And this should be 2, 3. And the last video we'll do for this first part is B3. And we're looking at this expression and we want to compute t beta alpha. So the first thing that we're going to look at is what happens to each of these basis vectors. So this equals 1, 0, 0, which equals 1 E1 plus 0 E2 plus 0 E3. T of 0, 1, 0, 0. This gives me 0, 0, 0, which is 0 E1 plus 0 E2 plus 0 E3. T of 0, 0, 1, 0 gives me 0, 0, or 0, 1, 1, which equals 0 E1 plus 1 E2 plus 1 E3. And last but not least, we have 0, t of 0, 0, 0, 1, which equals 1, 0, 0, which is 1e1 plus 0e2 plus 0e3. And this creates the matrix representation, T alpha beta equaling 1, 0, 0, 0, 0, 0, 1, 1, 0, 1, 1, 1, 0, 0. To compute the kernel, what we're going to do is we're going to use this matrix that we just created to create an augmented matrix that we set equal to 0. 1, 0, 0, 0, 0, 0, 0, 1, 1, 1, 0, 0, and we're going to set it equal to the 0 vector. And the solutions to this homogeneous system of equations can be used to generate the kernel. So the solutions, if we express them as coordinates vectors, they are the coordinates of the vectors that are in the kernel of T. So first thing we need to do is we need to do R3 minus R2, replacing R3 to convert it to echelon form. Now that it's in echelon form, we convert it back to a system of equations. And we have A plus D equaling 0 and C equaling 0 with free variables B and D and basic variables A and C. And we probably should have that we construct this by construct a system of equations by taking A T V1 or alpha 1 plus B T alpha 2 plus C T alpha 3 plus D T alpha 4 and setting it equal to 0. And that gives us this system of equations. Because we have our free variables B and D, we're going to let B equal S, which is a scalar, and here we're told that the scalars are the real numbers, so we need to let S be a real number. And D equal T, which is also a real number. Well, this means that A, B, C, D is now going to equal minus T, S, 0, T, which equals S, 0, 1, 0, 0 plus T minus 1, 0, 0, 1. So if we're looking at the solution to this homogeneous system of equations, so the solution space to the homogeneous system of equations is the span of the vectors minus 1, 0, 0, 1, and 0, 1, 0, 0. But what does this correspond to? The first vector, minus 1, 0, 0, 1, corresponds to if we look at our system of equations and what that means, if we take the linear combination of that vector, it corresponds to minus 1 t alpha 1 plus 1 t alpha 4 equals 0, which implies that minus 1 alpha 1, or t of minus 1 alpha 1 plus 1 alpha 4 equals 0, or minus 1 alpha 1 plus alpha 4 is in the kernel of t. And that means that one of those vectors is going to be minus 1, 1, 0, 0, 0, plus 1, 0, 0, 0, 1, which equals minus 1, 0, 0, 1. Now, if we look at 0, 1, 0, 0, this corresponds to 1 t of alpha 2 equals 0, which implies that t alpha 2 equals 0, which implies that alpha 2 is in the kernel of t. So here we have that minus 1, 0, 0, 1 is in the kernel of t, and 0, 1, 0, 0 is in the kernel. And these are a basis, these vectors form a basis for the set of solution vectors. So the kernel of t is going to equal the span of the vectors minus 1, 0, 0, 1, and 0, 1, 0, 0.